Hello, today we are looking at 2.9 logarithmic expressions, and we're going to kind of use some of the important concepts that we've talked about. So we're going to start by recognizing that every operation has one inverse or opposite operation. We learned inverse operations because this is going to allow us to be able to solve equations by utilizing what we know about the inverses and the inverse operations. So let's just start today before we get too much into our logarithmic expressions and just kind of recap a little bit. So let's say I had the operation addition. Then I might be talking about something like x plus 2 equals 8. Well, it does have an inverse operation, an operation that would undo that process. And that inverse operation is subtraction. So in subtraction, then that might look like 8 minus 2 equals x. What if we were looking at multiplication? Then that expression or that situation might look like something like 2x equals 8. So then if we want to know a little bit about the inverse operation, the operation that would undo that, that would be division. And so then that might look something like 8 divided by 2 equals x. And so that would undo that process. How about if we are squaring or we square a number? So if we square a number, then that might be something like x squared. That means squaring is the power. And we want to know something squared that equals, let's say, 8. Then its inverse, the inverse of square we learned is square root. That's the operation that would undo squaring something. And so if that's the case, then we might be taking the square root of 8 and trying to figure out what that is, which is not going to be a pretty number because that's not a perfect square. Then what about cubing? So if I cube something, then that means I have some value raised to the power 3, and let's say that's 8. Then the inverse operation to cubing we learned would be cube root. And so then we would have that little index of 3 there and our 8, and that would equal something. Okay, so we kind of went through lots of operations that undo each other. And today we're going to focus on exponentiation. And so exponentiation might be something like 2 to the x equals 8. Notice here the variable was down here at the base, but here the variable is the exponent. That's exponentiating. And so the opposite operation to that, the exponentiation, what would undo that is logarithm. And a logarithm, it would be something like log base 2 of 8 equals x. And so that's what we're going to focus on today is kind of working our way around those things and going back and forth between exponentiation and logarithm. So recently we learned about exponential functions, excuse me, and their properties. And we would like to solve equations involving exponential functions, which creates, as we've talked about in these situations, the need for inverse operations and the inverse operation related to exponentiation. So that's the verbiage that we want to make sure we know. So the big idea is just as we can write rational numbers in decimal form and fraction form, for instance, 0.5 can be 1/2, we can also write equations in exponential or logarithmic form. And the forms create equivalent statements that represent the same thing. So let's kind of start by just recapping a little bit. I'm not sure how much you remember about logarithms from Algebra 2, but basically logarithms were invented to simplify complex mathematical calculations, particularly multiplication, by transforming them into easier equations like addition, which was crucial for scientists and mathematicians before the inventions of the calculator and even the slide rule, especially in fields like astronomy and navigation, where large numbers needed to be multiplied very quickly. So John Napier, he's a Scottish mathematician, is mainly created with the invention of logarithms in the early 17th century. He published his work in 1614, and his approach was considered to be algebraic and was credited with speeding up calculations. Logarithms significantly reduced the time required to multiply numbers with many digits, and they were basic in numerical work for more than 300 years. And then from there, we started inventing mechanical calculation machines, slide rules, and then the calculator, the handheld calculator started out big piece of equipment, and now it's what we're accustomed to and working with today. And so then into that's in the 19th century, and then computers in the 20th century for large scale computations. So that's kind of the evolution of logarithms, but the concept of logarithm as an inverse of exponential, it kind of just extends our mathematical work as well. Kind of invented for the same reasons that things like square root were invented so that we could perform certain types of calculations and equations. Applications of logarithms, there are a lot that we don't even realize, but a logarithmic scale is used to deal with large range of values. So common applications for logarithmic functions are financial calculations, exponential growth and decay, radioactive decay, to find the pH level of a substance, to calculate bone mineral density, which is definitely a calculation used in biomedical engineering a lot of the time. Decibel levels in regard to sound, magnitude of an earthquake, which is used in the Richter scale. We can use it to help describe frequencies in musical intervals, and it can also aid in forensic accounting. So there are a whole lot of applications for logarithms that we might not even be aware of. Well, we're not going to get into a whole lot of that today. We are dealing with a lot of the mechanical workings of things today to make sure that you have all your skills and you understand how things work from Algebra 2, just in case we've forgotten anything. And so we're going to start our explorations of logs today. And we're going to be changing the problem, or we're going to convert back and forth between logs and exponents. And this is just simply rewriting the equation in an equivalent form. So we're not changing the value. We're not solving right now. We are just going to be switching back and forth because sometimes we might look at a problem and it might be easier to solve it exponentially. And in other times, if we convert it to a logarithm form, it might be easier to solve that way. So exponential and logarithm things get used in the same problems, in the same equations when you're solving. Sometimes it's whatever form is going to make it easiest to use. So that's kind of the big part here. So let's start with the exponential form. So if I have something b to the a equals c, then what are the parts of that? That b is the base, that a is the exponent, and the c is the output. That's the answer to the exponential form. Okay, when we're in logarithmic form, we find the base of the log right down here, and the symbols that we use, mathematical symbols, is log. And so b is going to be the base of the log. C is what we call the argument, and a would be the output to the log, which is actually the exponent. So remember that logs are another way of writing and using exponents in an easier form. So when we see that a is the output of a log is the exponent. Okay, so there are basically three parts to a log, and that's what we're talking about here. So we have b, which is the base, and the base of the exponent would be the same as the base of the log. Okay, and then we have this c, which is the argument in the log, but the output to the exponent. And so we have our a, our b, and our c, and then the a is the power in the exponent, and the output of the log. So these three things happen in whatever form you're talking about. Some of the wording is just a little bit different, but these are all things that you know, that A is the power of the exponent and A is going to be the output of the log, because all outputs of logs are exponents. And so they're connected together in that way. So being able to move back and forth, remember, is rewriting. It's not solving. It's not talking about undoing operations. It's simply just rewriting from one form to another. So as we go through this rewriting process, we do need to talk about some of the language and the notation that you're going to see. So in this notation section, the base of a log expression is 10. Okay. And when that base of the log expression is 10, that's what we call the common log. And it's written without a base number. So when we refer to common log, we don't need to write a subscript to represent the base. We will always know that that's base 10. So oftentimes it's rewritten without the base. For example, if we have log of 3 right here, then that is the same thing as log base 10 of 3. But you won't see the base 10 like it is right here. You're just going to see log of 3 because that's one of the most, well, as it's named, common log, right? So that's one of the ones that we use. The second one is when log has a base e. This is called natural log. And it can be written in two ways, just like here. So we, instead of using log, then we will usually use ln, and we'll say, let's say of x. Then that same thing would be the same thing as ln base e of x. So when we're talking about common log, we're talking about base 10. And that is an important distinction to make. So common log, base 10, and then natural log, base e. And so if you look at your calculator, you can actually see that there is a ln button, which means it only calculates in base e, and there is an log button, which means it only calculates in base 10. So your calculator is pre-programmed and set up to use these two keys for these two bases. Okay, so not everything are we going to need a calculator. Sometimes we're going to be able to use that concept of rewriting in a different form to be able to answer a question. But before we do all of that, I think we just should practice a little bit. So we're going to convert the following statements from exponential to logarithmic form. All right, so how do we go about this process? So basic rewrite says start with finding the log. So start with finding the base so we can write the log. So when I look at my exponent, I see that there is a base of 3 right here. So the base of the exponent will become the base of the log. So I'm going to write log and I'm going to do a little subscript of 3. All right, so then the output, remember, is the same thing as the argument in a log. So that means I'm going to have my 9 right there, and that's going to equal 2. So log base 3 of 9 equals 2. 3 squared equals 9. So those are two equivalent forms. So we converted it from exponential to logarithmic. Okay, so let's do the next one. So again, start with what's the base. So my base is 10. So I'm going to say log base 10. What is my argument going to be? Y. And then the output, remember, is the exponent. It's the power of the exponent. So that's going to be x. So the output of the log is the power of the exponential form. So this is one way you could see it, or you could just simply see log of y equals x, because we know when it's a base 10 that this is our commonly written form. Okay, so I'm going to have you pause your video and practice on C and D. So pause your video. All right, let's see how you did. So the base of my power is r, so the base of the log is r. The output to the x to the power is my argument, and the exponent is the output. Here, we have base e, so we know it's natural log base e. of y equals the exponent. And remember, when we say base e or we say natural log, we know that automatically that's base e. So you probably would see this written as natural log of y equals 3x. So that's going back from exponential form to log form, exponential form to log. So now let's work on going the other way. And, oops, sorry about that. And we're going to convert the equation from logarithmic form to exponential form. So from log, so you can see all of these say have the word log or ln, and then we're going to go to exponential form. So let's do the first couple together, and then I'll have you pause your video and practice the last two. So if we're going the other way, then we're going to start by identifying where our base is. So our base is right here. So that's 7, and that's going to become the base of the power. And remember, the output to a log is the exponent. So since the output right here is 2, the power is going to be 2, and that's going to equal x. Okay? And we could actually take this a step further and solve this. We could figure out what x is. 7 squared is 49. And so that is actually what x equals. And so we actually solved a log equation. All right, let's move on to this one. So then we look through our problem. Notice it's reversed, and that's okay. We're still first identifying what is that base value, and that base value is 3. So that 3 is going to be the base of the exponent. And then the output to a log is the power, and that equals the argument. So here is our expression. So go ahead and pause your video and answer C and D and make sure you're good there. We'll come back and compare. All right, let's see how you did. So remember, when you see this, this is what you're thinking. You didn't have to rewrite this. I just wanted to make sure that you remembered when you don't see the base, don't see that subscript, then that's 10. So then technically the base of my log is the base of my exponent. The output to the log is the power of my exponent, and the whole exponent statement equals the argument. And so again, we could go ahead and list if we wanted, because 10 squared is just 100. I didn't ask you to do that, but just taking that to the next step. So over here, there's no subscript visible for you. So we should know that that's base E because that's ln. So now we can rewrite it, e to the 4th equals c. These statements right here are not necessary. It's just wanting to make sure as you're going through these notes today that you're understanding where everything's coming from so that you have no problems. So evaluating expressions involving logs. Sometimes we can evaluate log expressions without the use of a calculator, just simply by rewriting it into its equivalent form. And so there will be times where you'll need to be able to do this without your calculator. And so you've got to rely on your ability to move back and forth between the forms. All right, so let's start here at what we have. We have an expression. Notice it's not an equation. It doesn't equal anything. So basically what we're thinking here is log base 2 of 8 equals something. And so in order to find the something, we're going to change the form. So what is the base of my log? It's 2. The output to the log is the power, so that's my something, and it should equal 8. So as I am working through this problem, then I can tell that I'm going to have 2 to some power, which is going to equal 8. So what is that something? 2 to the what power equals 8? That's 3. And so what we just found, this 3 right here, is actually the answer to the log. So that's 3. All right, let's practice another one. So what we're thinking here, because it's an expression, so log base 5 of 25 equals something. And so then we're going to rewrite it into exponential form to figure out what the something is. So we're going to have a base of 5, so that's going to be 5 to something equals the argument, which is 25. So then we're thinking 5 to some power equals 25. So what does that some power have to be? 5 to what power equals 25? That's 2. And so what did we just find? We found that log base 5 of 25 equals 2. And we did that through the use of changing it to its equivalent form. All right, go ahead and pause your video and work C and D, and then we'll come back and see how you did. Okay, so reviewing one more time, when it says to evaluate, that means to find the number that makes the statement true, and we're doing it without a calculator. So here, we're thinking log base 2 of 32 equals something. So 2 to the power of something has to give me the answer 32. And so I know 2 to the 8th power is 32. Therefore, log base 2 of 32 equals 8. It equals the power, remember. The output to a log is the power. So here we have log, and I don't see a subscript, so technically it's base 10 of 100 equals something. So 10 to the something equals 100. So what does that have to be? Well, we know that 10 squared equals 100. So log of 100 has to be 2. And so it's using that equivalent expressions, changing its form. Now, no, you don't have to write this statement down. That's just as we go through the notes and you're looking back, I want you to understand where everything came from. It's about understanding the position of all the parts of the logs and the exponents. So it's not just sitting down and memorizing. Now, not everything will be nice, pretty whole numbers like those first four. Sometimes you could have fractional exponents. Sometimes your exponent rules come into play and you know other things about what's going on as well. So for instance, let's look at E. So what is it saying? It's saying log base 16 of 4 equals something. And so if I rewrite that, remember, then that's going to be 16 to the something equals 4. Well, so immediately when I look at that, I have to think, if it's going from a bigger number to a smaller number, so right, a base of 16 is bigger than a base of 4, then I'm going to have something that's going to make that value get smaller. So hopefully you can recognize that we're talking about a square root right here. And so the power for a square root would be 16 to the 1/2 power is going to equal 4. And so what's the answer to my log? Log base 16 of 4 equals 1/2. So sometimes we have to work with the numbers that we have. We might have to change them to a fraction. We might have to use a negative exponent. In this case, we had to recognize that 4 is the square root of 16, and the square root is just the power of 1/2. All right, let's look at the next one. So log base 3 of 1. So log base 3 of 1 equals something. And so that means I need to know 3 to the something equals 1. Well, hopefully you recognize that that's one of our exponent rules, right? Because anything to what power is 1? So that has to be 3 to the 0 power equals 1. Which means log base 3 of 1 is equal to 0. All right, let's look at G. So once again, we're talking about a subscript of 10. So log base 10 of 10 equals something. All right, so log base 10 of 10 equals something. So then we're thinking 10 to the something equals 10. So what's the only thing that could be? 10 to what power equals 10? And that has to be to the power of 1. So 10 to the first power is 10, which means log of 10 is just the value of 1. So this last one is a little more interesting. We have log base 6, so not base 10, not base E, but log base 6 of 1 over 36. So we're going to kind of work through this in stages and apply some powers as we go. So the first thing that I am going to do is write log base 6 of 1 over, and since this is a 6 and 36 have something in common, I'm just going to go ahead and start by saying 1 over 36 is 6 squared equals something. Okay, so I have this fraction in here, and one way that we can address the fraction is we can make it a negative exponent. So we could say log base 6 of 6 to the negative 2 equals something. Makes it a little more user-friendly, if you will. And then let's go ahead and rewrite. So that means the base of my log is 6, so the base of my exponent is 6, and it's going to be to some power, and that's going to equal 6 to the not E, excuse me, guys. 6 to the negative 2. So I'm pretty sure that I can definitely see what that's going to be, right? Because that means for these to be equal and for our property of equality to be true, what's on one side of the equal sign has to be exactly the other. So I have 6 to some power equals 6 to the negative 2. So the power on this side has to also be negative 2, or that equal sign doesn't work. So then I can come up here and say this equals negative 2. All right, so that's using what we know about rewriting an equivalent form to be able to work through these problems. Now we're going to do a little bit of calculator practice. So we're going to use the calculator to evaluate the following expressions, and we are going to include at least 4 places after the decimal point. So not just 3, but 4 this time. So go ahead and pause your video. If you don't have your calculator handy, run and grab it, and then we will work through these 4 problems. Okay, so now that you have your calculator, we're going to look right here. And so notice whenever we're dealing with ln, we're going to press this button right here. And when we're dealing with log, log base 10, we're going to press this button here. So to do log base 9, then I'm going to press the log button. And then I'm going to push in the number 9. So that's how we go through the computer here, the calculator. So we're going to press log, and you can see it opens a parenthesis. So then I'm going to type in the 9. If I were doing a series of calculations, I would want to be sure and remember to close that parenthesis. But if you don't have anything behind it, then it will be okay because there's no other numbers. If you don't close that parenthesis, anything behind it, it will also take the log of that value. So then when I hit enter, I have 0.954242594. And we said we were going to go to at least 4 decimal places. So then I'm going to say that's approximately 0.9542. All right, so base 10, easy, use the LOG button and type it in. So let's go ahead and do the next one. So we're going to press the log button, and then we're going to press in 6125. If there's nothing behind it, you can leave it open. I typically just am in the habit of closing it just because I don't want to mess up when I need to. And so when we hit enter, then we can see we have 3.787106093. So we're going to go 4 decimal places after the decimal. So my answer here is going to be approximately 3.7871. And what we put in the calculator, again, log button, and then we typed in 6125 and closed that parenthesis out if it's a longer list. Okay, so now we get to C, and C is a little different because it has base 2, not base E or base 10. So typically what we actually have is a rule here called change of base. And so if you want to take it out of log base 2 and be able to use that log button on the calculator, then we have what's called change of base. And so what that means is we're going to take the log as log of the argument, which is right here, so that's 10, and we're going to divide that by log of base 2. So the base of the log is the base of the fraction, or the bottom, where basements at in houses, they're down in the bottom, all those kind of things. So this is actually what's happening on this calculation. So we can say log base 10, close the parenthesis, divided by log base 2, close the parenthesis. So when we do this operation called change of base, it gives us this answer. So we know that this is going to be approximately 3.3219. Now, with our new calculators, we do have a template that we can use, but I wanted you to understand this first because I do get people that don't use the template. They just find it's easier to type it in like this and keep going. But the calculator does have a template for you to use to do any other base besides 10 or E. You get to that by pressing alpha. That's the green button. And so you're going to press alpha, and then you're going to press window. And then you're going to pick number 5. And number 5 is log base, and it has that parenthesis. So when I pick number 5, now you can see it actually gives me a template so I can type it in just like it looks in the problem. So I'm going to say log, and I'm going to have this bottom box, which is going to be my base. So I'm going to type in a 2, and then I'm going to have this box right here, which is going to be my 10. And so I can actually enter it just like it looks by putting a 2 down here and putting a 10 in here. And so what's happening is the calculator is doing this right here to do your calculation, but it's actually allowing you to enter it in the form with which it looks on your paper. So you can use that template. So this is change of base. This is for anything that is not base 10 or base E. And so the change of base rule is doing this. This is how you enter it and use the multiple base template. All right, so you do problem D. You can use whichever way you want to do it. You can do the division and turning it in with change of base, or you can use the template on your calculator. So pause your video and do this one real quick. Okay, so I worked it both ways. So you could see if you do the change of base formula, you get the same thing as if you use the template. And it truly doesn't matter which way you want to do it, but you need to make sure you know how to do the way that you're going to do and be sure that you understand it's not magic. Typing it in this template isn't just poof, magically it happens to be 2.5208. It happens to be 2.5208 because the calculator is taking the log of 135 and dividing by the log of 7. So no mystery there, just straightforward log property. One useful purpose for logarithms is when we're dealing with exponential data. So exponential data can be kind of hard and challenging to get a decent graph because in exponential data, you could have values that start really small, but then they grow really fast. And so what often happens then is it's difficult to create a display that effectively shows small values along with extremely large values all together. So this particular set of data is the population of English America in the United States since 1620, and it's grown exponentially. The estimated population from between 1620 to 1820 is down here on these two graphs. So population is your vertical axis, and the years is your horizontal axis. And so we're having an initial T of 0 value represents the year 1620. So when time is 0, which is right here, that's the year 1620. And so as we plot data, the vertical axis is 1 million, 2 million, 3 million, 4 million, very, very big numbers. Then we have the growth from year to year. And if you look right here in the beginning, it's really hard to distinguish what might be happening between these two because you're having such a small unit on your horizontal axis. You're representing years, and you're only looking at the years from 1620 to 1700. It's just almost indistinguishable what's happening vertically. We know it's all less than, these values here, but that's it. And so then all of a sudden then you hit here and you can see the nice pretty curve because those values are a little more spread out. So the one to the left shows the population in a normal scale on the vertical axis, and the population is expanded into millions, and the data points represent the years 1620 to 1700, and it's really difficult to notice the difference in population during those beginning years. So these years right here, right? It's really hard to tell what's going on there. And even kind of up into here until it starts spreading out and you can see the growth pattern a little bit better. Well, if we look at the right, and that's this population right here, we use a logarithmic scale. Okay, so the logarithmic scale is base 10 for the vertical axis. So here the vertical axis is base 10. Here it was on a normal scale. And we used a logarithmic scale to show us and the data points converted here. And so as you can see, because we don't have this stack up right here where they're all right there together, we can start to see that curve immediately, and we can have a little more information based on those points as it curves. So the data points are easier to distinguish, or the relative between the two, and it's easier to read. So one common type of graph with logarithmic scale vertically. So this is going to be in logarithmic scale. And it oftentimes you'll see these grid lines that go across here. And so those grid lines are representing the log scale. And then these vertical lines are representing the coordinates. So we're going to just practice plotting. We're going to use and see this graph more. The logarithmic scale is the vertical axis, and that's where the grid lines are. So that's representing the log. And then the coordinate on the bottom is the second piece. So we will see this again. We will come back and do some more logarithmic graph. So this is just kind of a little introduction. So all we're doing right now today at this point is just getting comfortable being able to actually read the two different scales, the logarithmic scale here and the grids for the axis horizontally. And this is not giving you any scales on anything other than we know that this one right here is a log scale. Okay, and this one isn't. Okay. So on the first one, we're going to go 1, and then we're going to go 20. So 1 is right here. Here's 10. And then the first line up, because this is log scale going from 10 to 100, which means this one right here would be my 20. So that's my point A. Okay, so now we're going to graph point B. So then we're going to go to 2. And then when we get up here to 100, remember now we're going from 100 to 1,000. So that's 200, 300, which is going to be right here. And that's going to be my point B. All right, so go ahead and pause your video one last time and plot points C, D, and E, and then we'll come back and compare. So how did we do? So we started at 3, and then we're going from 1 to 10, so that means we're on this line right here. On 4, we're going to 15, so we hit 10, and the next one would be 20, so 15 is going to be right there in the middle. And then finally, number 5 is 350, so I go up here to 100, and then it's 200, 350 is right in between. So remember, the horizontal lines on this particular type of graph are giving you a scale for the logarithm, and then the horizontal is just the placement of the points. All right, so what we've accomplished today is we have reviewed what we know about logs from Algebra 2. We've practiced converting between the form. We've started beginning talking about that if it's an inverse situation, then we can use that undoing operation to solve equations, although today we didn't actually solve any. That's just kind of introducing for things to come. We talked about how to use the calculator for when we need to do an log base, an ln base, and then any other base. And we definitely looked at the properties and the pieces of the log, so we can definitely go back and forth. And then we kind of talked about the natural log is base E, and log is the common log base, which is 10. And so for those two bases, we won't see subscripts. All right, and then finally, we just practiced doing a little graphing on our new graph paper that has a log graph on the vertical axis. All right, so you should be able to work on your daily practice, and we will see you next time. Thanks, guys. Bye.